Welcome to Mr. Bixel's Tutorials. This is a conservation of energy problem. 12 kilogram rock is perched on the edge of a 250 meter high cliff, and it falls when it strikes the ground below. Right here, it's going 60 meters per second, and it would be going faster, but we're assuming air friction impeded its descent. How much energy was dissipated into thermal energy on the way down? So how can we solve this? Well, first thing we need to do is draw a nice picture. Characteristics of a good picture: shows the rock, has its mass, shows the height of the cliff, shows the rock at the bottom. This part here isn't necessary, but I've done it for a reason. I wanted to show you the rock getting faster as it goes down, and also to be able to talk about the acceleration. Because air friction plays a part in this problem, we can assume that air friction gets bigger as the rock proceeds closer to the ground because it's going faster, and thus this acceleration right here will not be constant. Because it's not constant, we can't solve this with kinematics equations. You may think that x final equals x initial plus v0t plus 1/2 at squared will work, but that assumes that this acceleration is constant. So we've got a problem here. Kinematics won't do it. Time for conservation of energy. The next thing we want is an energy flow diagram. That's this right here. And the event here is the fall of the rock. The system includes the rock, the earth, and the air, right there. And the energy before the event, the fall, is entirely gravitational potential energy. And after the fall, when the rock gets all the way down here, we're assuming it's close enough to the ground that its height is negligible, so it will have no gravitational potential energy after, and then it's all translational kinetic energy and thermal. This diagram right here provides the basis for us to organize our calculations. So, the law of conservation of energy, if we're going to assume that the law of conservation of energy is true, energy before equals energy after. The energy before was all gravitational potential energy. The energy after is translational kinetic energy and thermal only. So we just follow through with the calculations. We know the formula for gravitational potential energy is mass times gravity times height. Mass of 12 kilograms, gravity 9.8, height 250 meters. We get 29,400 joules. On the other side of the equation, we now need to think about the translational kinetic energy. That's energy after. Translational kinetic energy is here, 1/2 mv squared. We plug in the mass and the velocity after the event. We come up with 21,600 joules. So we have this equation. The total energy before is 29,400, and the total energy afterwards has to equal 29,400. Subtract 21,000 joules from both sides, and we end up with 7,800 joules equals thermal energy after. And we can go back and check that. If we were to plug in 7,800 joules there, and then add 21,600 to 7,800, we'd come up with 29,400. So that's the solution. How would I suggest you practice? You need to write down only the word problem from above, attempt to solve it on your own without looking at the solutions, and then check your answer. That's it. That's the conservation of energy problem number 1. Thank you for listening. This has been Mr. Bixel's Tutorials.